Welcome everybody to our next video presentation in our Probability and Statistics series. Again, I am Dr. Latham, and you can find me in the Department of Mathematics at Missouri Southern State University. So let's get started on today's lecture on dice, poker, and craps. So let's begin with a definition of a discrete probability density function. So a discrete PDF is defined on a discrete sample space, and by a discrete sample space we mean it is either finite or countably infinite. So a discrete PDF is a function P on S into the real numbers that satisfies two properties. First of all, that the probability of any value in the sample space is always going to be non-negative, and second of all, that the sum of all of the probabilities for every element in the sample space will be 1. And so remember, just as a little bit of review, that our probability function is actually defined on an algebra of sets, and our algebra of sets in this case we said would be the power set, so the set of all possible subsets of S. And for that we can extend our function P to the power set by saying that we'll define that the probability of any set E is going to be the sum of the probabilities for all of the elements that are in E. And so this gives us the probability of a particular event. So now let's be a little bit more concrete with the definition that we just had. So the experiment that we'll deal with is just rolling a standard six-sided die. So we're only going to throw it one time, and the experiment will be recording the number of spots that occur on top as the particular outcome for the experiment. So probably you know, with standard six-sided die, our sample space is just going to be 1, 2, 3, 4, 5, and 6. And if the die is fair, then the probability density function is what we call a uniform distribution, that the probability is going to be the same independent of the value that actually comes out. So the probability of getting a 1 is equal to the probability of getting a 2 is equal to the probability of getting a 3, all the way up to the probability of getting a 6. So if we got 6 possible outcomes, same probability for each one, then the probability is just going to be 1/6. So now, to see how this actually works with an event, so let E be the event that the number of spots has remainder 2 when we divide by 3. Okay, so we look at the elements of our sample space and we say, alright, well, what's the remainder of 1 when I divide by 3? Well, the remainder of 1 is 1. What about the remainder of 2 when we divide by 3? Well, the remainder of 2 when we divide by 3, sure enough, is 2. So 2 is going to be an element of our set E. Remainder when we divide by 3 is 0. Remainder when we divide by 4 is divide 4 by 3 is 1. Remainder when we divide 5 by 3 is 2. So we found another element of our sample space, or of our set E. And then finally, if we divide 6 by 3, we get remainder 0. So the only two elements in our sample space for this particular event would be when we roll a 2 or we roll a 5. And so if we're looking at the probability that this actually happens, well, the probability of E is going to be the sum of the probabilities of all of the elements in E. And so if we look at the probability of 2 plus the probability of 5, we get 1/6 plus 1/6, which gives us a probability of E of 1/3. Now, probably if you're familiar with dice, you know that the standard six-sided die is not the only kind of die that we can have. We can have Platonic solid dice. Platonic solid dice are going to look something like this, where the tetrahedron, so the blue one, is going to have 4 sides to it. The cube, that's our standard six-sided die. The octagon, which is going to give us the green one, has 8 sides. The dodecahedron, the yellow one, is going to have 12 sides, and the icosahedron, the purple one, will have 20 sides to it. So the Platonic solids actually give us a geometric realization of a uniform probability distribution. So if we calculate the uniform distribution, so one thing that you can do, I'll leave this kind of as a challenge, calculate the uniform distribution for each one of the Platonic solid dice, but then for the event E that we just defined, where we get a remainder 2 when we divide by 3, calculate the probability of E for each one of the Platonic solid dice. Now, if we do that, just to give you a heads up, here's what the answers that you should get. You should get 1/4, 1/3, 3/8, 1/3, and 7/20 for the probability of E for each one of these Platonic solid dice. So also, as you know, that quite often we don't just roll one standard 6-sided die, we're going to roll a pair of them. And typically we're going to be interested in the number of spots that actually show up, so the sum of the spots that actually show up on each die. So let's see how we might analyze that particular problem, which has some interesting characteristics that we're going to use for the remainder of our discussion on probability and statistics. So what does the sample space look like? So we're supposing that we're rolling 2 fair dice. Then the sample space X we can write, or the sample space S we can write as an ordered pair. So the first entry in the ordered pair is going to be the value that we get for the first die. The second entry in the ordered pair is going to be the value that we get for the second die. And so that's going to give us a total of 36 possible ordered pairs in the sample space. So again, if we're assuming a uniform probability, so any combination is going to be equally likely, so a uniform probability distribution on this sample space is just going to be 1/36 for any particular ordered pair that we have. Again, we aren't really interested in one particular ordered pair. What we're going to be interested in is the sum of the spots and not the particular values on the dice themselves. So this experiment, we've talked about the ordered pairs, but how do we then get to the sum of the spots? So the way that we actually get at the sum of the spots is to use something called a random variable. Now, the random variable will end up being one of those super important concepts that we're going to use throughout our discussion of probability and statistics. So, what is a random variable? Well, a random variable is nothing more than a function. So, it's a function on the sample space. So our sample space S, that set of ordered pairs, we've got this function from S into the set 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that function is defined as really the sum of the first entry of the ordered pair and the second entry of the ordered pair. So we are getting the sum of the spots on the die. Well, now how do we actually get a PDF for this function z? So how do we get a probability density function for the function z? Well, we'll do that in the following way. Somehow we want to tie this back to a subset of our sample space. And so we'll say, well, what's going to be the probability of getting a 6? Well, we'll look at something called the preimage of 6. So the preimage of 6 under this function z is going to be the set of elements in our sample space that get carried to 6 when we apply z. And so now we don't know necessarily how to find the probability of 6, but we do have the probability for each one of these ordered pairs. And so what we can do then is to say that the probability of rolling a 6, so the probability that the z value is going to be 6, is going to be equal to the sum of the probabilities of all of the entries in the sample space that get sent to 6. So all of the elements that are in the preimage of 6 under z. So that's going to give us the probability of the ordered pair 1, 5, plus the probability of the ordered pair 2, 4, probability of 3, 3, probability of 4, 2, and probability of 5, 1. So if we add all of those together, then sure enough, we get the probability of rolling a 6 being 5/36. And so let's say that we were interested in computing the probability of rolling a 7, or the probability of rolling an 11, or even let's say the probability of rolling a 7 or an 11. So if you kind of use this same idea of looking at the preimages of all of the elements in the sample space that have an image under z of 7, that's going to tell you, well, how many ordered pairs is that going to have, how many ordered pairs are going to have an image of 11, and how many ordered pairs are going to have an image of either 7 or 11. Well, if we add those up, then the answers that you should get of probability of 7 should be a 6th, probability of 11 should be 1/18th, and the probability of a 7 or an 11 should be 2/9. And so remember, when we're rolling 2 dice, that we're representing our sample space as all of these ordered pairs. So we got 36 ordered pairs. If we look at the probability of each one of the values z, so z being the sum of the spots, so the sum of the entries in the ordered pair, then if we calculate those out, we get these probabilities of particular combinations. So if we look at the probability of rolling a 7, then we get 0.166666667. What that would actually correspond to, if we come over here and look at the set of ordered pairs, that is going to correspond to rolling a 7. Then we've got 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6. So those all correspond to rolling a 7. So that gives us 1, 2, 3, 4, 5, 6 of those. So if we look at the decimal expansion of 1/6, sure enough, we get 0.1666666. Likewise, if we wanted to get the probability of rolling an 11, well, we just look at which ordered pairs end up giving us a sum of 11, and so 6 and 5 gives us 11, but also 5 and 6 gives us 11. So probability of rolling an 11 is just going to be 2 out of 36, which gives us 0.055555555. So if you want to, as an exercise, go through each one of those probabilities, confirm for yourself that sure enough, those are the values that we will get for the sum of the spots on our dice. So now, as another example of using random variables, let's introduce another game. So let's suppose that we have 3 urns labeled A, B, and C. The urns contain different balls, different numbers of balls with the following counts. So the first urn, urn A, has 7 white balls and 11 black balls. Urn B has 9 red balls and 5 green balls. Urn C has 6 red balls and 10 green balls. Now, here's the question. So the game is played by drawing a ball out of urn A. If a black ball is drawn, then the player will draw a ball from urn B. But if a white ball is drawn, the player will draw from urn C. So urn A is used to determine whether we're going to really get the ball out of urn B or urn C. 2 balls are going to be drawn without replacement from either urns B or C. A red ball will be given a total of 2 points, and the green ball will give you 3 points. So the question is, calculate the probabilities of the scoring outcomes for the game. So probably the best way to visualize this particular experiment is again using a tree structure. So the first level in our tree, below the root node, is going to be earn A. So earn A was going to tell us were we drawing from earn B, or are we drawing from earn C. So earn B, or earn A actually, contains either black balls or white balls. So the probability of drawing from earn B is actually going to be 11 over 18. We had 11 black balls, and we had 7 white balls. So the probability of drawing a black ball is going to be 11 over 18. Probability of drawing a white ball, 7 over 18. So then, for our first draw, if we drew a black ball, so that we come down to this node, then we had 9 red balls and 5 green balls there in earn B. So the probability of drawing a red ball on the first draw was going to be 9 out of 14. Probability of drawing a green ball on the first draw was going to be 5 out of 14. Now, had we drawn a white ball from earn A, we would be drawing from earn C. Well, in earn C, we had 6 red and we had 10 green. And so the probability of drawing a red ball, had we drawn a white ball, was going to be 6 over 16. Probability of drawing a green ball, 10 over 16. Now here, remember that in this particular situation, we are drawing without replacement, so that now our probabilities change. If we've drawn a red ball, then on the first draw, well, we've got one less ball to actually draw from. So we go from having 14 balls to having 13 balls. We've drawn one of our red balls, and so we started out with 9. So for the second draw, our probability of getting another red ball is going to be 8 over 13. Likewise, we only have 13 balls left, but we still have all 5 of our original green balls because we drew a red ball. So the probability of drawing a green ball once we've already drawn a red ball is going to be 5 over 13. So if we can kind of continue that analysis, we've got started with 14 balls, we're down to 13, and for each one of those situations, we get the probabilities for our second draw. Now, we're kind of visualizing our sample space as being a set of triples. So the first one being the first draw from earn A, the second two being what we draw from either earn B or earn C. So it'll be either 2 reds, a red and a green and a red, or 2 greens. And so our sample space actually has 8 elements in it. And so how we would visualize the points in this particular game is again as this random variable. So we have a points function that will map from our sample space into the set of possible outcomes. So we get 2 points for a red ball, 3 points for a green ball. So we can either have a 4, a 5, or a 6 as our possible outcomes. So in this particular case, if we look at the probability of getting 4 points, well, let's look at which paths are actually going to give us 4 points. Well, the only way we can get 4 points is to draw 2 reds. So that's going to correspond to this path, or it's going to correspond to the path where we draw a white one and then draw 2 red ones. Well, remember that the probability along any path is going to be a product of the probabilities along that path. So that was coming from our definition of conditional probabilities. So the probability for the first path, we're going 11/18 times 9/14 times 8/13. The probability along this path, we've got 7/18, 6/16 times 5/15. And so if we add those two together, we get 3,805 over 13,104. So an approximate decimal expansion of that gives the probability of getting 4 points of 0.2904. So I will leave it to you as an exercise to then compute the probability of getting 5 points and the probability of getting 6 points. Now let's talk about our poker a little bit. So here in this setting, we're not going to talk about Texas Hold'em or anything like that. So we're just assuming that we're playing standard 5-card poker. And so if we look at the rankings of types of hands that we can have and their respective scorings, we get a list here of 10 possible outcomes. Well, if we just look at the total possible number of hands that it can be dealt from a standard deck of 52 cards, so 52 cards, now we're going to get to use our binomial coefficients. So we've got 52 cards, we want to choose 5 of them. Well, there are 2,598,960 ways that we can be dealt one 5-card hand of poker. So now, as an exercise, let's compute the number of possible types of hands that we can have in this particular game. So these kind of calculations are all over the internet, but let's kind of compute some of them for ourselves. So let's talk about straight flushes. So what do we mean by a straight flush? Well, we've got all the cards are in numerical order, but in addition to being in numerical order, the flush also has to be, all the cards have to be from the same suit. So either hearts, diamonds, spades, or clubs. So that really gives us a straight flush. Now a straight flush, they've got a higher type of hand called a royal flush. So a royal flush has a particular ordering to it. There you get a 10, a jack, a king, queen, and an ace. So we're going to assume ace is high. Well, we're not going to worry about those. We're going to calculate the non-royal straight flushes. And so we'll do that by listing all of the numerical orders that we can have for the cards. So here we're assuming we've got ace is high. So we've got values of 2, 3, 4, 5, 6, 7, 8, 9, 10. Then our jack, queen, king, and ace. So if we're talking about a non-royal straight flush, then we can look at the positions. So the lowest position for the card in the hand. Well, the lowest position that we can have could be either a 2, a 3, a 4, 5, 6, 7, an 8, or a 9. Now if we had a position of 10 as the lowest card, well, now we're talking about a royal flush. So here we're looking at non-royal straight flushes. So these are the possible positions that we can have. So if we were going to look at how many of those we actually have, well, again, using our binomial coefficients, we've got 4 possible suits that we can have. And so how do we choose that? Well, 4 choose 1. But then also, in choosing the starting position, we've got 9 possible starting positions, and then we choose one of those starting positions. That gives us 9 choose 1. So kind of the attributes that determine what a royal or what a straight flush is going to be will be your starting position and the suit that you are using. And so kind of 2 different independent choices for those. So our total number ends up being the product of those 2 numbers. So 4 choose 1 gives us 4, 9 choose 1 gives us 9. So we've got a total of 36 possible. So 36 possible non-royal flush straight flushes. So the second type of hand that we'll calculate the numbers of will be full houses. So our first question is kind of going to be, how do we characterize a full house? Well, a full house consists of three of a kind of one type of numerical value, and then a pair for a second numerical value. So the number of full houses that we can have. Well, we need a numerical value for our first kind. Well, we've got 13 different numerical values, 2 up through 10, then Jack, King, Queen, and Ace. So we've got 13 different numerical values, and of those once we choose the numerical value, we've got 4 different suits, and we want to choose 3 of them. So this is choosing our 3 of a kind. So that combination is choosing our 3 of a kind. What about choosing our pair? Well, for choosing our pair, we've got 12 remaining possible numerical values. So of those 12 remaining numerical values, we want to choose one of them. But since we only want a pair, we've got 4 possible suits, and we want to choose 2 of them. So this particular combination gives us the number of ways of choosing our pair times the number of ways of choosing our 3 of a kind. So if we got 3 ways of doing one experiment, or this number of ways for doing one experiment, this number of ways for doing the second experiment, then the product of those gives us the total number of ways for the experiment. And so if we multiply that out, we get 3,744 full houses. And so the probability of getting a full house is going to be 3,744 divided by the total number of 5-card poker hands that we can have, which was 2,598,960, giving us a probability of 0.00144. So kind of putting that into context, if we have only one deck, then on average we will only see a full house about one or two times out of every 1,000 hands that were dealt with. Now let's look at the number of ways that we can get 2 pair. So let's begin with our description of what actually is going to characterize getting 2 pair. Well, we can say that we get 2 pair. We have one pair of one numerical value and another pair of a different numerical value, and then we've got a single card of a third numerical value. So if we want to get 2 pairs, one way of calculating this is say, alright, well, we need 3 different numerical values. So of our 13 possible numerical values, we're going to choose 3 of them. Now, of those 3 that we've chosen, we need to choose 2 of them to be the ones that we're going to use to get the pairs. Okay, so the 3 choose 2, we're choosing 2 of them to get the pairs. And then in choosing the pairs, we've got 4 suits for each card, and we want to choose 2 of them. So 4 choose 2 for the first card, for the first pair, 4 choose 2 for the second pair, and then finally, for the last card that we have, we've got 4 different suits, and we just want to choose one of those cards. And so that's going to give us 4 choose 1. If we multiply all those possibilities together, then we get 123,552 ways that we can get 2 pair. So if we look at that probability, so the probability of getting 2 pair is going to be that number over 2,598,960, or approximately 0.0475. So again, putting this kind of in context, if we are using only a single deck, then we will only see getting 2 pair on average about 5 times for every 100 hands of poker that we are dealt. So then to put that kind of in context, if we look at, so for each one of the types of hands that we have, we get a royal flush. There's only 4 possible ways of getting a royal flush, which we get an incredibly small probability for. Straight flush, we figured 4 of a kind, not too much better. Full house flush, a straight, in which all of the cards have increasing numerical value, so you get 2, 3, 4, 5, 6, something like that. But for just a straight, which is not a straight flush, the individual cards in the sequence could be different suit values. Probability of getting 3 of a kind, 2 pair we did, and probably the most interesting 2 are getting the probability of getting a pair or getting nothing at all. That we get a huge increase. So if you're playing poker, chances are you are going to see somebody's going to get a pair about half the time, so about 4.4225, or your probability of getting absolutely nothing at all is just a little bit bigger than a half. So if you put those 2 things together, your most likely hands of poker will be either you get a pair or you get nothing at all. So now let's kind of come back to our dice games and look at the rules of craps. So how do you play craps? Well, the game is played in 2 rounds, either the come out round or the point round. So for the come out roll, a couple of things can happen. So the player is either rolling a 2, a 3, or a 12. So if on the come out roll you're getting one of those values, it's said that the player craps out. And so that's kind of another way of saying, oh, the player loses. Okay, so the player loses their bets if they roll a 2, a 3, or a 12 right out of the box on the very first roll. If they roll a 7 or an 11 on the come out roll, then this is automatically a win. If they roll any other values, so any other values other than 2, 3, or 12, 7, or 11, so if they get a 4, a 5, a 6, an 8, a 9, or a 10, then this is what's called the point. And then the second phase of the game begins. So in the point phase, the shooter is going to continue to roll until one of 2 things happen. Either the player rolls the point again, in which case the player wins, or the player ends up rolling a 7 and the player loses. So this is basically the game of craps in a nutshell. Let's see if we can do a mathematical analysis of this game. So again, a wonderful way of analyzing this game is again using our tree structure. So we're kind of interested in winning or losing this particular game. So how the game is played can be analyzed with a tree. So the first level in our tree is going to correspond to the come out roll. So on the come out roll, kind of 3 basic things can happen. Either the player is going to win, so we get a W. The player is going to lose, he craps out, so we get an L. Or we get a 4, 5, 6, 8, 9, or 10, and these correspond to the different points that can be established. So either we win, we lose, or we set the point value for each one of those. Well, let's look at the probability of winning on the come out roll. Well, for winning on the come out roll, we either have to get a 7 or an 11. Well, from our previous discussion, we said we know what that probability is going to be. Well, for a 7, we get a 6 out of 36. For an 11, we get 2 out of 36, and that ends up giving us a probability of 1/9 for our winning on the come out roll. Well, what about losing on the come out roll? Well, if we crap out on the come out roll, that means we're going to get, we've rolled a 2, a 3, or a 12. Well, if we look at the probabilities of getting a 2, we've got 1 over 36. Probability of getting a 3 is 2 over 36. And the probability of getting a 12 is 1 over 36. So the sum of all of those gives us the probability of crapping out on the come out roll, and so we get 1/9. And for the other values, either getting a 4, a 5, a 6, an 8, a 9, or a 10, again, that's just what's the probability of the sum of each one of those spots. So for a 4 or a 10, we get a probability of a 12th. For the probability of getting either a 5 or a 9, we've got 1/9. And the probability of getting a 6 or an 8, we each have 5/36. So now, once we've established the point, so let's say, for instance, just for the sake of argument, that we've rolled, we didn't crap out, but we established the point at a 9. Okay, well, what's going to happen from there? Well, now one of three things is going to happen. Either we win, in which case we roll another 9, we lose, in which case we've rolled a 7, or we get any other number and we have to roll again. Okay, so the probability of winning with the point being set at a 9 is going to give us 1/9. Probability of losing is the probability of a 7th, of 7, so we get 1/6. And the remaining probability of having to roll again is actually going to be 1 minus 1/9 minus 1/6, and so we get 13/18 for having to roll again. Now, the interesting part of this game is that, well, who says that we have to roll again? If we roll, then what can happen? Again, on the second roll, we could either win, we could lose, or we roll again. Or we win, we lose, or we roll again. And so what really can happen is that we can have this infinite tree. So once we set our point value, we get this infinite progression of possible trees for infinite number of rolls. Now, yeah, that's not really going to happen in real life. Sooner or later, we're probably going to roll a different one. But again, we are dealing with strictly theoretical probabilities, and in our strictly theoretical probabilities, we could have an infinite tree for each one of these point values. Well, how do we go figure about the probability of winning in that case? Well, let's analyze what happens in the tree. So the probability of winning, given that the point is established at 9, is going to be, well, how many of these paths end up giving us a W at the end of them? Well, we can either roll a 9th, so it corresponds to that path. We have to roll again, and then we roll a 9 again. So that's going to give us the probability of rolling again, 13/18 times a 9th. Or we roll again, then we get the point value so that we finally win. So that's going to give us 13 over 13/18 squared times a 9th plus ... So for every level in our tree. Well, what this ends up giving us is an infinite series. So we get this infinite series of 1/9 times this series from k equals 0 all the way up to infinity of 13/18 to the kth power. So we get this geometric series. So maybe from Calc 2 you might remember, or some other previous math class, that you've seen the sum of a geometric series. Well, yeah, we know how to do that. The sum of a geometric series is just going to be 1 over 1 minus whatever value we've got in here that we're taking the power of. Because with our geometric series, our power had to be in between 0 and 1 so that the thing converged. And so that gives us a sum of 1/9 times 1 over 1 minus 13/18. And so the probability of winning, given that the point is established at 9, is only going to be 2/5. And so now if we do that for each one of the possible point values, well, if the point is established at 4, the point is established at 10, we end up having an infinite series, which is like 1/12 times a geometric series with our ratio being 3/4, and so that's going to give us a probability of 1/3 of winning if the point value is either 4 or 10. If our point value is 5 or 9, we get a different geometric series. We get a geometric series with a ratio of 13/18. And so that's going to give us a probability of 2/5. With the point being established at 6 or 8, we get a geometric series with a ratio of 25 or 36. And so that's going to give us a probability of 5/11. So now, what is the probability of actually winning a game of craps? Well, if we look at all possible ways that we can win. So the probability of winning on the come out roll, we get 2 knights. Or we're going to establish a point. So here the points, 1 point value for all the possible point values. We get our probabilities that we're putting in here. And so ultimately, our final probability of actually winning a game of craps will only be 0.4929292929 repeating. So that's kind of interesting in that your probability of winning is going to be less than half, slightly less than a fair coin flip. And so what we actually might say is that the most probable winning move when playing a game of craps is to actually not play at all. So hopefully this has kind of given you a little bit of an introduction to using some of our counting formulas, using a notion of probabilities, and using our notions of random variables in doing some calculations with some real games. So I hope you've enjoyed this. Maybe we'll do another game, another video on craps to actually do a little bit of simulating with R to see that, yeah, our probabilities actually do come out the way that we think they should. So stay tuned for that. Hope you guys enjoyed this. Talk to you later.